This conference will now be recorded.
So very good evening, students. Today we will be concluding the NEET UG Physics paper 2023. So let us finish this discussions on this particular paper. Today we have some 9 questions over here. We'll quickly solve all those and discuss. So let us start with this one. So the first question says, a horizontal bridge built over a river. A student standing on the bridge throws a small ball vertically upwards with a velocity 4 meters per second. The ball strikes the water surface after 4 seconds. Height of the bridge above the water surface is. So the question is, suppose you have river like this. Okay, water is flowing like this. Okay, and on top of that, a bridge is made. Okay, over that bridge is made. Okay, I can take something like this. Okay, so suppose this is a bridge above the water. So this has, see, suppose this is the water level, and you have got certain height from the water level. Okay, you have got certain height over the water level. So I'm just uh, trying to make you understand that there was a boy who was standing here itself. Okay, who was standing here and throwing a ball. Okay, upward, throwing a ball upward. I'll demonstrate here. Suppose this is the water surface, and this is the height of the, this is the height, say this is h. Okay, say this is h height, h, and this is the water surface. Okay, this is water surface of the river. Now this is the height of the bridge, h. Now a boy is actually standing here. Okay, the boy is standing here, and he is throwing a ball straight upward. Okay, upward like this. He is throwing the ball with certain initial velocity, that is 4 meter per second. 4 meter per second. Okay, now the question is, the ball strikes the water. See how it goes, it goes first some top. Okay, it momentarily comes to rest, and then it will be eventually falling on the water. Okay, like this. This is the ball. This is the trajectory of the ball, somewhat like this. Okay, so this ball is, when ball is touching, suppose here time starts at t is equal to 0. When it was thrown upward, time was 0, and when it falls over here on the surface of the water, this is 4 seconds. Now the question is, what is the height of this bridge above the water surface? So this is the question. So how do you solve this problem? See, we'll be using kinematics equation. Kinematics equation. Which equation do you want to use? We want to use, see, y if this is the height minus y0, this is the initial height, is equal to ut plus or minus half acceleration into t square. This is the formula we are going to use over here. Okay, so you might be thinking why I'm writing this y0. See what I'm just taking this point as the starting point. This point as the starting point, and when I start the motion, if already some displacement was there, that particular displacement I will be writing as initial displacement as y0. In this case, maybe I can write as h0. This is the initial displacement. Initial displacement. Okay, initial displacement. Okay, initial displacement. So look here, initial displacement, if I write this as h, this is the initial displacement is h here, right? So initial displacement here, initial displacement, okay, displacement is capital H, right? And what is the final displacement? See, I'm taking the height. See, h is equal to 0 over here. That means final height, it is actually on the water surface. Ball is falling on the water surface. So final displacement, which I have written here as y, that is here 0. Final displacement is 0. Okay, that means see y is equal to 0 here. 0. Final displacement. It is final displacement. Okay. And what is u? U is the initial velocity. And see, in this case, by default, what I'm taking the height as positive in the, like, above the, or in the upward direction, I'm taking height as positive, and downward direction I'm taking as negative. Similarly, the u, the velocity, initial velocity, I'm taking as minus above the, or like upward direction, I'm taking minus, initial velocity minus in the upward direction, and the acceleration acts on this is the g. The acceleration act over here is the g. Okay, because see, when it goes to the maximum height, it becomes rest, and with any initial velocity 0, it will fall down freely. So this is actually free fall under gravity. So that's why the acceleration will be downward, but I am just taking the motion from here. I'm starting the motion from here. So in this case, I should take g as negative. Okay, like acceleration as negative, I'll write it down here. So acceleration a is minus g, and initial speed, initial speed or velocity, let us say initial velocity is equal to minus u over here. Okay, I'm taking minus u because it is thrown in the upward direction. So that is the reason. Okay, now look how this formula could be written for this particular problem. See, the final height 0, the initial height h, then t is given as 4. Okay, so u is here how much, 4, along with the minus sign, and t is 4 again. Okay, this is 4, and see here acceleration is negative because the motion of the object is in the upward direction. I'm just considering the whole motion starting from this point. Okay, that's why I'm taking g by default, like acceleration by default negative. Okay, so this is g with along with half, and t square, t is 4 square, and see here g we have to take as 10. So I'm writing here 10 meter per second square. Okay, now look what I get here. I get in the, okay, I get in the left hand side 8 if I just multiply negative sign uh, both sides. So what I would get, so I think I have done a small mistake. I'll take the velocity, since it is thrown upward, I'll take this velocity as positive. I'm sorry for that. So this speed will take as positive. Only acceleration will be taking negative. Okay, this will be taking positive alone, because this motion we have given in the upward direction. Let us be happy with that, with the speed u itself. And here, so then it is 16. Here there will be minus sign over here. 16 minus 80. Okay, so which again can be simplified as 64. So this is the thing. Okay, I think I'll not confuse you much more. So I just want to clarify that the velocity, since it is given in the upward direction, let us say that is, let us take that as positive, and acceleration, since it is acting in the downward direction, let that be taken as negative. Okay, acceleration g. Okay, the motion is in the upward direction, velocity is given in the upward direction, so velocity, let us take this as positive, but acceleration will be always acting against this velocity, so we have to take this as negative. So that's the clarification. Now you might be thinking, see, I'll just even if you don't think, I'll just ask you a question over here, just to clarify, like just to make your understanding little more sound. So this is the river water surface. See, the boy, when the ball was thrown in the upward direction, that time was 0, and when it falls here, it is 4 seconds. Okay, but obviously during the whole 4 seconds, see what we have done, we have used ut plus or minus half at square. This I have used. So that means, this time has been taken as if during the whole duration, the object just has displacement this much. Okay, but it is not true, right? The object just gone up, then it just covered this distance. See, the object gone up, then it has to come down up to this height, and then it is actually coming down. Okay, not the whole 4 seconds. Actually it covers only this distance, less than 4 seconds, isn't it? But we have taken 4 seconds in this expression. You look here in this, while solving this problem, we have taken just 4 seconds. Why? How it is going to be all right? How is it going to be all right here? See, you can answer me that I have taken the initial situation over here at this position and final situation here. That's how I am taking the whole time. That is fine. Time was fine, but it is actually uh, it is actually covering this much displacement, right? It has this much displacement and coming down. So here is the clue that if I take positive upward direction, then some y1 suppose the same distance, it is coming down in same time. Okay, in same time, and that is also minus y, that I have to take minus, because displacement has a direction. So if I write here, look, h plus, this is the, so it covers h plus y minus, sorry, y1 minus y1. So ultimately how much displacement we are getting? We are getting the displacement h itself. Okay, that's how it is going to be all right. Okay, during this time interval, the total displacement, it is not the distance, it is the total displacement, that is h, because this displacement positive while going up, and while coming down, that will be negative. And when you take the average or the sum of all the displacements, so you will get 0 for this contribution. That is the reason we just take 4 Second, the whole displacement is just h. Okay, so this question may arise in your mind, so I have cleared that. We'll go back to the answer here. See, 64 meter, so the option B will be the correct answer for this case. Okay, so 64 meter. Now we'll go to the next problem. So this is also a very interesting problem and easy also. A satellite is orbiting just above the surface of the Earth with period t. If d be the density of the Earth and g be the universal constant of the gravitation, the quantity. Oh, I'm sorry. The quantity. There is a quantity. I'm just writing it. The quantity. See, the quantity is 3 pi by g into d. G into d, where d is density, this quantity represents. So here somehow I missed this. So 3 pi by the quantity, and this quantity is here. Okay, 3 pi by capital G and d for density here. So this quantity represents whether it is t square, t cube, square root of t, and t. So what it is, we have to answer this question. See, this is the satellite as you see in this figure. Suppose this is the satellite. Oh, this is the satellite. Okay, this is the satellite which is orbiting just above the Earth. Okay, that means we can take the orbit, like the orbital radius of the satellite to be small r is equal to the radius of the Earth itself. Okay, nearly that, just above it is said. So that's how we'll take this. Now look, now this is just like a circular motion. See, so this is the center of the Earth. So the whole mass of the Earth is here, and whole mass of this satellite is here. Suppose the satellite has small mass, and this is capital mass, like mass capital M, and this has small m mass. So we can write, see, and one more thing, let us say the orbital velocity of the satellite is v. So I can write mv square by r. See, this I could have written small r plus r. See, I could have written small r plus capital R. Since it is just above this, so small r, so the small r plus capital R, that I am taking as capital R itself. Okay, and this will be is equal to, see, this centripetal force is given by the Earth's gravitation. So G capital M small m by R square. Now look, this cancel. So V orbital velocity will be actually root over Gm by R. So here m is the mass of the Earth. Since mass cannot be like it has mass cannot be same, but density is uniform. So mass can be replaced by this. Earth, we have considered the Earth as a sphere, solid sphere of radius capital R. So this into d is the density. Okay, d is the density. So if we put it here, let us see how we get and what we get. See, 4 pi r square d by 3r into m. Sorry, into g. Let this be here. We can just do a little bit of simplification. So this can be written as 4 pi r d by 3. Here g will be there, obviously. Oh, I'm sorry. This gm by, so gm, this will be here, it will be d, and g also will be there. the numerator. That is g by 3. Okay, 3 pi by gd. Okay, so this is one thing. Now what is time period? Time period is 2 pi r by v, right? So we can just write t square as, see, we can write this as 4 pi square r square by v square. Okay, if I write this, look, I have an advantage to put the value of v square. So v square means, see, v square is this, so 3 will go in the numerator, and see, this is v square I'm writing here. V square I'll put directly, that is 4 pi r d and g. Okay, so this is this. I'm just putting directly v square from here. Okay, so v square is this value I'm putting here, and let this be here like this. Okay, so now we can just do a little bit of simplification. So this goes along with 1 pi, and this r v 1 pi, 2 pi r by v. Okay, so okay, let us see how it goes. dg, so we have got, but there may be a small, okay, I'm sorry, see, this here, this is the volume I have to write. So this is r cube. So here will be eventually r square. Okay, so this will be r square. Okay, here it will be r square. So if this is r square, then there will be no r. So 1 pi will be there. So see, the value will be 3 pi by g d. This is equal to t square. So if you, so I have given you a brief idea and also solved it. If you feel like it is messy, you may just try by yourself. So this is the term 3 pi by gd, which is equal to, or which represents the t square of the time period. Okay, now we'll go to the next question. Okay, this is again an interesting question. It is from semiconductor chapter, so digital electronics part. See, these bubbles actually represent the NOT operation. Represents, this bubble represents NOT operation. So it is, say, it is A. That means, you know, this output will be just A bar. This is B. So when uh, see, we see the output, it will be B bar here. So this A bar and B bar is fed to this gate. See, what is this gate? This is again NAND gate, and NOT operation. That means, see, NAND gate, if I have two input A, B, this NAND gate, what it gives, you know, that this will give you, see, A dot B and bar of that. That means, you know, A bar plus B bar, it will be. Okay, NAND operation is this. So in this case, look, my inputs are A bar and B bar. So let us write first AND of A bar and B bar, and then a whole bar of that. So this gives actually, see, from De Morgan's theorem, we can write, or De Morgan's rule, we can write A double bar plus, so this dot or AND will be OR, AND becomes OR then, this. So this double bar, see, A bar means, suppose, see, the input is 0, bar means 1, and see, double bar means what? Input was given 0, 0 again inverted to 1. That means it will be actually A double bar is becoming A itself, and B double bar is becoming B itself. So what is the output here? Output is this. Now see, we can just see from this output, like which of this table is satisfying this output. See, for the first table, see 0 0, if we give input 0, see A 0 and B 0, obviously OR gate means output will be 0. That is fine. So this is fine. Now since it is OR, if any one of these gates or input is on state, then the gate will give like result on itself. See here, one input, see input A is 0, but this is 1. That means one switch is on, another switch is, sorry, this switch is off and this is on. That means since it is this represents actually parallel combination or gate. So in case of OR gate, if any one of the inputs are at on state, then the output will be on. So here, look here, this 0 plus 1 in simple algebra, also 0 plus 1 is 1. Again, if the A is 1 and B is 0, hence in this case also output will be 1 only. So this is 1. If both are on in parallel combination, if both are on, then the whole circuit is on, like the output is on itself. Okay, so then this is the correct truth table. Other truth tables will not satisfy this. See, A is 0, B is 0. Would you get one output? No, if both are off, then this represents off state only. Okay, but here look here, this says one is off, another one is on. Then in case of series or AND gate, it will be 0, but OR gate it will be 1 itself. So this is also not true, this is also not true, but this is true anyway. Again, this is not true. So the whole truth table is not applicable for this gate. Okay, we'll go to the next problem. So we have got the correct answer, option A. Okay, so this is again an interesting problem, and also it is a thoughtful problem. We need to think it and solve. So look this question or read this question properly. A very long conducting wire is bent in a semicircular shape from A to B. See, A to B is semicircular as shown in the figure. The magnetic field at point P for steady current configuration is given by. See, I'll tell you there are parts of this total configuration. So this wire is semi-infinite. See, one side is infinite. See, one side is infinite, another side is finite. So this side is finite up to A, and this side is actually infinite as dot says here. So this is infinite, and this side is finite. So I can have wire like a finite wire, one side finite, another side infinite. So this is called semi-infinite wire. So these wires both are these. So these straight portions are actually not infinite wire; they are semi-infinite wire. Whereas this is actually an arc, semicircular arc. Now, Biot law. What Biot law states, in the sense, Biot law has a final format or formula to find out magnetic field at any point due to a steady current through a wire. Sorry. Yes, so be here. See, this is actually net magnetic field. If I have if I have a semi-infinite wire at any position which is having a perpendicular distance r from that wire, so the net magnetic field is to be mu0 I by 4 pi r sine phi 1 plus sine phi 2. You just go back and read the Biot-Savart law. So there it is derived. So I'm not deriving here, but for see for semi-infinite wire, one of these angle will be 90 degree, another angle will be 0 degree. Let us say phi 1 is 90 degree, another one is 0 degree. So this B net due to straight portion, in this case semi-infinite straight portion, magnetic field will be B net is equal to mu0 I by 4 pi into 1. Okay, so this will be the magnetic field. Okay, at this position is r, so this distance is just nothing but r itself. Okay, P is r. Okay, so that's how we get magnetic field due to the semi-infinite portion, and there are two portions, so I'll write here this. Okay, so I'll get mu0 I by 2. Let me write 2 over here itself, just to keep a uniformity in the result. I'm writing this. Now look, you have got certain direction of magnetic field. I have written the magnitude due to these two wires itself. Now let us see whether the magnetic fields are at this point due to both the wires are in the same direction or in the opposite direction. If they are in the opposite direction, they may cancel also each other. So effect of magnetic field over here due to the semi-infinite wire. See, if you use right hand thumb rule, so you look the magnetic field due to these two contributions will be into the plane of the page. Okay, into the plane of the page, into the plane of page. Okay, so the magnetic field due to this semi-infinite wire at this particular point is into the plane of the paper. Now due to this arc, see, first of all, circular arc, for circular arc, for circular conductor, a conducting loop, magnetic field at the center. In this case, look, if I just consider this as this is the whole circle. Okay, whole circle, then it may have certain radius of curvature. Okay, so we'll write that conductor. So the circular conductor so for magnetic field at the center, that means P point is at the center. Okay, so when it is at the center, the magnetic field in general, what is the magnetic field due to circular loop? B, I'm writing the circular loop, circular. In general, magnetic field will be mu0 I by 2, mu0 I a square here by 2 into a square plus x square whole to the power 3 by 2. That means if you have a circular loop like this, in general, magnetic field will be at any point of the axis of this this loop will be given by this formula. If this point P is at distance x here, and this radius is a, okay, then the magnetic field is at this point will be like this, and it will be along the axis of the rotation. Now look, in this case, what is this A? A is given as R, radius of the loop. Okay, and what is X? At the center, X is equal to 0. Okay, X is equal to 0, A is equal to R. So if we put it here, look how we get circular loop. For circular loop, magnetic field will be mu0 to a q. Okay, so finally you look mu0 I a square, I'll cancel them out. So at the center of the circular loop, generally it will be the case mu0 I by mu0 I by 2 a means the radius, in this case it is R. Now look, it is a semicircular arc, so that's why it will be again getting half. So for semicircular half, see B net at P is due to this will be, because due to semicircular wire means I by, so that the magnetic field will be getting half. So 2 into R. Okay, that means mu0 I by 4 R. Okay, this will be the magnetic field at the center due to the semicircular arc. Okay, now look. So what is the net magnetic field at that position? See, due to the circular arc, the magnetic field is coming out. Okay, and it seems to be having greater magnetic field. Okay, greater magnetic field. mu0 I by 4R. So magnetic field, net magnetic field at P will be so net magnetic field is actually mu0. So let us write this mu0 I by 4 pi mu0 I by 4R minus, because this is actually coming out of the page, and the other part has magnetic field how much, that is 2 mu0 I by 4 pi R, 2 mu0 I by 4 pi 2 mu0 I by 4 pi R. 2 mu0 I by 4 pi R. Okay, so this is actually into the plane of the page. Okay, so if we do a little bit of simplification to get any of these this type of this, so we'll write mu0 I by R or 4R, mu0 I by 4R, so 1 minus 2 by pi, 1 minus 2 by pi. So this is answer, and also this is actually out out of plane of the paper. Okay, so out of the plane of the paper and or away from the plane of the paper, look this one, mu 0 I by 4 pi 1 minus 2 by pi pointed away from the plane of the paper or away from the page. Okay, so we'll move on to the next problem. So here answer was the B. Let us see this problem. The resistance of a platinum wire at 0 degree centigrade is 2 ohm. That means, okay, let me read fast. And at 6.8 ohm, so 6.8 ohm at 80 degrees centigrade. The temperature coefficient of the resistance of the wire. See, for platinum resistance or any or resistance for conductor with temperature, how it varies? It varies like R0, so which is the temperature at 0 degree centigrade, whole into 1 plus alpha. Alpha is the temperature coefficient of resistance into T. Okay, this one. All right, so this T can be centigrade also, doesn't matter. And now look what we can write. R of T, which we have, this is at 80 degrees centigrade, T is 80 degrees centigrade, minus R0. R0 means at T is equal to this, and I'm going to calculate alpha. So this will be alpha, sorry, R and T. Okay, so this R0 is given as 2, so RT is given 6.8, okay, minus R0 is 2 per second. I'm sorry, these are actually ohm, in ohm, divided by RT, that means 6.8 into T. T is 80 degree again. Okay, 80 degrees centigrade. So let us not write degrees and all here, we'll just take as value. So if you solve this problem, you know what you are going to get. So it is, yes, so let us do that. 6.8, and this is, that means 4.8 divided by 6.8 into 8t. So 24, and here it will be 34. Okay, that's how. This is 17, and this is 12, and 12, this 4 and 20. So anyway, if you just solve it, it will be around 3 into 10 to the power minus 2 per degree centigrade. This is per degree centigrade. All right. If I have done any mistake in the calculation, please correct it and see. Calculation part is just as homework. You can do it. Now this question is also very simple. So an electric dipole is placed as shown in the figure. So what is that? See, this is the figure. This is the dipole. That means, you know, dipole has length 2L is equal to 6 centimeter, or let us say this is L is equal to 6 centimeter, and at the middle, so this is the middle, and this is 3 centimeter, this is 3 centimeter. Anyway, the question is the electric dipole here shown in the element, and see the electric potential electric potential at P due to the dipole is. So this is the point which is from origin, it is 5 centimeter away from the origin middle point of the uh, dipole. So in this case, you know the how to find out potential. Potential anyway, we know Q by 4 pi epsilon not R or distance. So in this case, see the potential at P will be Q by 4 pi. I'm taking the positive, Q by 4 pi epsilon naught positive. So it will be, see, this much distance alone. That means we can then subtract 5 minus 3. So it will be just 2 centimeter. Okay, so it is 1 by R. That means 1 by 2. Okay, and similarly, due to this, I would write due to positive Q, and this is due to negative Q at P. At P, so this much distance is added to that. Okay, 5 plus 3, so 8 Q by 4 pi epsilon naught into 1 over 8. Okay, now if you just add these two, okay, VQ plus at P, VQ minus so VQ plus and minus, so this term is anyway common, Q by 4 pi epsilon naught 1 minus 2 1 minus 8, which turns out to be 3Q by 8, and see this is 1 by 4 pi epsilon naught, so I can write that as K. So ultimately 3QK by 8. I'm sorry, here it is this option. So this is how we have to solve the problem. So we have got few more problems. Let us see that. So this is again an interesting problem. See here in this figure, see this figure, there is a lens, right? That is actually dipped into some liquid. So in the figure shown here, what is the equivalent focal length of the combination of the lenses, assuming that all the layers are thin? So this is 1.6. That means it is anyway something else. The 1.6. This is the glass, thin glass. We can take 1.5. Okay, so which is given here, and since it is dipped in the medium, some medium. See, for this we have got a formula. Since the layer are thin, so we have got this formula to find out the focal length for this kind of combination. And when that combination or lens itself is deep into the liquid, see here 1 by f, that is the focal length, I'm just assuming, and this mu2 is the refractive index of the medium in which it is dipped. Okay, and say mu1, oh no, I'm sorry, this mu2 is actually the refractive index of the material of the prism, sorry, length, material of the lens, and this mu1 is actually refractive index refractive index of the medium. Okay, here it is actually having this much. So 1.33 generally for water, 1.5 is for glass. So in this case, look, if I apply this formula, how it goes. See, 1 by f, I have to find out f. So mu2 is given as refractive index of the medium, that is refractive index of the material of the prism, so that is 1.5, and medium minus 1.6 here, and whole into 1 by r. See, in this case, r1 and r2 both are 20 centimeter. So this is 20 centimeter. And see, this here is the interesting point. See, the r1 is actually having positive value, and this has negative value. So I can write minus 20 here. Then we get minus 0.6 into 2 over 2 over 20. Okay, 2 over 20. This is positive. Okay. So from here, actually, we'll be obtaining 0.1. See here, not 0.6. This is 0.1. That's why the mistake was. Okay, this will be actually minus 100. Okay, so minus 10 centimeter. This will be the answer. This is very simple. This is very simple. A wire carrying current I along positive x direction. Say this is positive x direction, and it is carrying current I, and it has length, some length L. It is kept. This is kept in a magnetic field. So some magnetic field is there. So when there is conducting wire in the magnetic field, so it will be experienced by, or it will experience certain magnetic force, and that can be written as B is equal to B is equal to B ideal cross I dl cross R. I'm sorry, in this case, ideal cross I. Oh, I'm sorry. Here, actually, the magnitude of the magnetic force. Magnitude of the magnetic force, ideal cross B. I dl, so IL cross B. This is the magnetic force. So eventually, if you find out, see, L is actually in the positive x direction. So I'll write L in the positive x direction, in the sense I cap direction, and cross B is 2 I cap plus 3 j cap. So we'll take the mod of this force. Obviously, this mod will be square root of 5 IL. Square root of 5 IL, you will be able to find out. Oh, I'm not. No. I'm sorry. This will be actually 25 inside the root, so it will be 5 IL. 5 at 5 IL. You can just use IJKL cyclic formula and do this calculation. You will be able to find it. Okay. So the last question for today's session is this: X the graph of a particle performing simple harmonic motion is shown in the figure. The acceleration of the particle is this much. Oh, sorry. The acceleration of the particle at 2 seconds is. See, this is a simple harmonic oscillator. You can just do one thing. You can just take this displacement as A sine omega t. Okay, then take the single derivative to find out acceleration. If you don't have the acceleration, in the mind, so you can just do this derivative part. Okay, here like the a omega cos of omega t, then double derivative for accelerations minus a square, sorry, this is omega square x, omega square x. Finally, it will be omega square x. So what is the displacement? What is the acceleration then? Acceleration at 2 seconds. See, I have to put one by one value. So first of all, what is the omega? Omega is the angular frequency. So here in this case, directly it is not given. See, it has given in the other way. So this is the time period. It has got time period time period as 8 seconds, or let us say some simple 8 without any 8. So what is omega? Omega is equal to 2 pi by t. So 2 pi by 8, and see, if I write omega square, this is whole square, so you will get 4 pi square by 64. So here it will be pi square by 64, and here minus is there, along with that minus will be there. So pi square by 16, I'm sorry, pi square by 16 with a minus sign. What about this x? X is at this time x is how much? I'm sorry, the 2 second x is 1. So x is 1. We can put it here as 1. Okay. So that's the answer. We have got pi square by 16 meter per second square. Okay. So this is the whole discussion on the JE NEET JE UG paper 2023. Discussion is over today. We'll pick up again some new things in the next class. So thank you for your patience. Bye for till then.